Hey, Paul, appreciate the intro and hope everybody's healthy and staying warm. It was single digits here this morning, and just before my daughter and I were out playing around with the heifers a little bit, and the sun was out. So in Michigan, to have the sun in January, February is always a good thing. I was asked to talk about just the impacts of our work in terms of grazing and carbon. And as you guys know, it's probably a hugely um, question. There's a lot of back and forth on this in the literature, in the press, and the media. And I always want to emphasize that what I'm presenting is data from our own context, right? Like data that we've been collecting at a farm or two in central Michigan, and with very unique climate, with unique rainfall, potential to grow quite a bit of forage, and really some ideal conditions to be able to look at how what our management does to improve ecosystem services. Many of y'all are from more of the central part of the north central region, and based on your climate there, based on the moisture, your ability to cycle litter and nitrogen through systems, your data is going to be considerably different from ours. And so again, this is not a silver bullet. It's just what we've been working on here. And I think principally speaking, management principles can be applied everywhere. It's just that the outputs and outcomes might be somewhat different based on where you live. And as we all know, there's always been a real level of debate about grazing management. I can go to the literature. I can find really high quality scientists that do good work, and they can articulate that for, in this case, holistic planned grazing, but other grazing management schemes, whether you call it management intensive or adaptive multi-paddock, whatever the flavor of the term is, doesn't have a lot of impact on building carbon in the soil. Perhaps doesn't have that much impact on productivity or animal performance. I can likewise often go to the literature and find that enteric methane we all know, is a key contributor to climate change. It has a high global warming potential. And because of the fact that cattle put quite a bit of it into the atmosphere, what we need to do to stop this and to therefore curb potential for global warming is to reduce livestock numbers, and reduce them dramatically and reduce them globally. And then also finally, even if we can build carbon in soil, that it's going to become quickly saturated, right? Like, and that means that the mineral in the soil can only bind so many carbon molecules. And once it does that, they're not going to be able to do that anymore. And so it's going to quickly become saturated like a sponge. But equally interesting, I can go to the literature and find that there are improvements in applying grazing strategies to the land. I can find in a multitude of papers, including some from our lab, that grazing can sequester carbon in significant amounts. There's work out there that also says often methane can be more tertiary in terms of a beef model, and that's multiple fold. It can be that our models that predict methane overestimate them, which is common. But likewise, the global warming impact is considerably different. Methane's a short-lived gas atmospherically, and normally has a half-life of 10 years. We put it on a 100-year global warming potential. And so based on the literature you look at, you can find completely opposite things. And then there's a fair bit of literature out there to suggest that we've lost so much carbon that good management has the potential to bring quite a bit down. And you know what? Our ground has been so depleted, it's going to take a while before saturation becomes a worry. And so it's really interesting that we have this back and forth in the literature, and you can find good people, good science that come up with different outcomes. And that's where a lot of this debate, I think, goes back and forth, and it's contextual. It's how we do the science, and it's probably not going to end anytime soon. Where we work primarily is Lake City Research Center. It's on the 45th parallel, not far from Traverse City, if you're familiar with Upper Michigan, Northern Michigan. We're fortunate, man. We've got 600 grazable acres. Across this place, we run about 300 or so red Angus animal units, stockers, yearlings, and cow calf pairs. And I've been managing this place since about 2009, 2010. And what we've been really trying to do is to be demonstrative and observational in a lot of our science. We also have 64 acres of replicated pastures where we do more intensive research. And we just try to do a blend of demonstrative, but likewise perhaps more reductionary approaches to answer certain questions in terms of our observations. Generally across this place, we've got 9 GPS areas across sand, loam, and clay that we typically do our long-term monitoring on. Um, and we're ramping up to do some exciting things hopefully here in the near future. So we've been measuring carbon, we've been measuring methane, we've been looking at the efficacy and the efficiency of grass finishing beef in these models. It Again, we're in a very unique area. I get about 35 inches of rain. When we started here, our organic matters were 2 to 3. They're probably closer to 4 to 5 in a lot of those areas that we're at now, 10 plus years later. Um, we I've kind of fallen into this term. I'm really awfully tired of the nebular vernacular of grazing, but for this talk anyway, I'm going to use adaptive multi-paddock grazing. And full disclosure, I work with Savory Institute as we try to provide the institute a level of scientific knowledge that we try to help in terms of analyzing data. And we have a holistic context. We do those sorts of things, but generally speaking, I kind of fallen into using this term, adaptive multi-paddock. It's kind of an overarching term, probably irritates people, and for that I apologize. But the basic premise of cattle and carbon is the fact that when we manage our grazing, and what I mean by that is managing to recovery, meaning that we allow animals to defoliate, to apply animal impact appropriately based on what the management wants, and appropriate to the landscape, appropriate to the goals of the manager, that we allow for adequate recovery. And so what we tend to see in those models is that cattle productivity can potentially increase based on where you are. Generally speaking, that provides greater vegetative and lower lignin type grasses, which, although there is considerable methane coming out of that system, it's less than other types of systems. And so it can be pretty productive. And because of the way that we graze, we also can stimulate greater plant growth. We get more roots below ground, more shoots above ground. We can also potentially see perhaps in reduced erosion, and we see improvements in terms of microbial life as well. That can, in many situations, then improve soil carbon, the sequestration, and that's a function of root turnover. It's a function of bringing nutrients into the soil. It's also a function of nitrogen. If I had to like briefly say the kinds of recipes or the kinds of things you need to help build carbon in your soil, it's going to be your inputs, right? The litter layer, it's going to be carbon and nitrogen. It's going to be water. And then of course the microbial activity and the activity that happens below ground simultaneously, right? But I do want to say that these management strategies are all really predicated on full recovery of plants. And what we mean by that is the roots have recovered from a prior defoliation. The plants are approaching a reproductive stage yet again and have had ample time to fully recover. And concurrently, then that allows for more sensitive species in a biological niche to become more competitive. If we graze more aggressively, if we don't graze to full recovery, often we just select for the grasses that can take harder grazing or more intense grazing and can tend to put biodiversity backwards. And so finally, another unique aspect of this, I think, is that in certain situations, we can see increased perennialization of forages. And a lot of that too, I think, is because of reduced species selection. By increasing your stock density, you have the opportunity to more uniformly defoliate an area. You know, the range in these impacts are highly variable. Really love some of the CARM work that's coming from the ARS out of Wyoming and Colorado. And they perhaps not seen some of these impacts as highly as what I've documented here. Whereas in our context, we tend to see them more. Now, I can potentially run 250 to 300,000 pounds of density per acre in a system, where concurrently in those landscapes, their stocking rates could be 10 or 50 fold less than ours. So you run into these aspects of time and spatial variation, right? That in certain environments, you may or may not see the impacts. And perhaps those impacts are occurring, but because of the vastness, it's difficult to monitor and to pick those up from a standpoint of taking soil cores or other things like that. This is one paper that we've got in the literature from Ag Systems. I'll briefly talk about on our grass-fed model, and the reason I'd like to do this is I would like to show you how changes in carbon can ultimately influence beef cattle's overall footprint. This is the primary grad student on this paper was a young lady by the name of Paige Stanley, who's now trying to wrap her PhD up at Berkeley, and is did a lot of this work. But what we did effectively in this project is we actually took 5 years of our actual data from our grass finishing model, and then on top of that, we put our soil monitoring with that. Our primary soil scientist for this project was Dr. Marcia DeLong, who's with the Union of Concerned Scientists, also trained at Berkeley with Dr. Wendy Silver. And so effectively what we did is we tried to look at the impacts and compared a grass model versus a grain-fed model in the upper Midwest. And so what you would typically find in the results of this project is that, hey, when you look at productivity and emissions, a feedlot is going to be about 50, perhaps 30 to 50% more efficient from an emissions perspective on a kilogram of beef basis. And that's just normal. A feedlot is considerably more productive. It requires less land. Generally, our models would say maybe about 0.4 acres to finish one beef animal. And concurrently, those carcasses are also heavier. So what happens then is you need less cattle, you have less emissions per unit beef, but you also have more intensity and more perhaps unintended consequences on a bigger frame when you look at the feedlot model. We've been, again, applying some level of managed grazing to our system. And what we found compared to the other literature is when we applied adaptive multi-paddock grazing, we actually found that our emissions were 45% lower than most of the literature that were looking at more continuous grazing or grass finishing models. And so we saw significantly less emissions, shorter finishing times. We also attribute that to greater forage quality. And in this case, I also want to bring up is that we quit using nitrogen in our forage-based models 10 years ago. We have done a little bit of cover crop grazing, and I've used some nitrogen there. So again, this is kind of what the math looks like, right? Grass finishing is always going to have a higher methane footprint. And generally grain-fed is going to have more feed emissions. The manure is somewhat the same, okay? So in this case, about a 30% reduction in overall emissions per kilogram of beef comparing a feedlot to our grass-fed model. But what then happens if we were to apply carbon, okay? I want to be clear in the fact that 10 years ago, we inherited a farm that was aggressively grazed, that was aggressively hayed, had a pretty high stocking rate, and was also had routine fertilizers, managed very conventionally. We stopped that model and imparted a model that was more ecologically driven. It was more management driven. It was predicated on recovery. And we really focused on trying to stack things that might improve ecosystem services. And so what we found in our first 5 years of measuring is that we saw about a 3 to 3.5 metric ton of carbon per hectare per year sequestration. And when you apply that to our grass-fed model, what we actually see then is that model becomes a sink. Now, importantly, I don't have the cow side of the equation in this. I've caught heat for that, for being incomplete. The paper in of itself was an actual novel. It's a long paper. It gets more and more complex. I mean, you can throw so many variants into this if you want. You could say, hey, if we regeneratively graze the cows, we'll see those improvements on the cow side. Land use becomes a significant issue. And I want to employ that generally these models are going to take and in our context, 2 to 2.5 times the same amount of land to produce the same amount of beef. So there has to become a debate on how we look at land and agriculture. There is a component that would say, hey, we need to absolutely have an intense agriculture system to provide more wild spaces. There's others that say that regenerative ag, or ag that's working to improve the ecology simultaneously, can provide biodiversity. It can provide greater pollinators, more birds, more grouse, more prairie chickens, whatnot. So, then that this type of agriculture is an agriculture we need to see more rampant and more adopted. And so, effectively, just to shut this paper down, this is 5 years of data on one farm. We use full accounting LCA. And when we use soil into this model, it dramatically changed the outputs. Okay. Again, there's trade-offs. Land use is one, competition for arable land is another. But we do summarize that well-grazed cattle can have a role in sustainable food systems. Okay. And so that's one thing I'd like to talk, to summarize on that paper. The next thing I'd like to briefly talk about is where we are in terms of methane today. This is a paper that we had published, a review of the literature by a young man who's on the verge of finishing his PhD. He's going to go to work for Dr. Kim Stackhouse on a postdoc at Colorado State University, where we did a pretty thorough review and where we are with methane in the literature. And methane is another hot button, right? And again, methane it's a byproduct of microbial fermentation in the rumen. Basically, we have these free CO2s and hydrogens that are that byproduct. We have volatile fatty acids that are given off in terms of for metabolism for the cow. And methane is a byproduct. That methane goes up in the atmosphere. And as you can see up top, right in here, there's about a 12 or so year length of time that methane is broken down in the environment. When methane is broken down, it's concurrently hydroxylated by OHs and broken back into hydrogen, H2O, water, and carbon dioxide. And it is recycled through photosynthesis and through rain events, right? And so it's very much a natural system. This is the same system that built the soil, carbon, and the prairie. Where things have gotten skewed is that we've brought other forms of methane into the atmosphere that are not part of natural biogenic cycles. So therefore, these aspects and these challenges become more conflated. Does that mean that we shouldn't worry about methane in cattle? I don't think so. I think we should continue to work with our grazing management, which is the key way that we can lower methane. And then also other technologies that might make cattle more efficient to have less enteric methane as well. 98% of methane is eructated. A couple percent is out the back end. I can't tell you how many calls I've gotten from press and media and politicians about the cow farts killing the world, right? And just like perplexing that it's simplified to that level. This is the old way where we measure methane using SF6. It's a way that we've done for years here at Lake City. We've now even use green feed tools where basically there's NIR that is built into these pieces of equipment. I've got a kind of a small weather vane here. I've got a hopper I put alfalfa pellets in. A cow comes in with the EID, drops some pellets. There's a vacuum in here. It sucks. She keeps in this hopper for about 5 minutes, something like that. She's breathing. She's eructating in there. It's sucking it up. We have NIR that's measuring the methane. Then finally, we have a data logger and a hotspot that is uploading that into a database where we measure methane. One thing I want to point out is based on our data that we often find that due to increased forage digestibility, among other things, intake differences, we typically find that methane can be, somewhere between 15 up to 35% less than what the typical International Panel of Climate Change methane prediction models say. And that's a big number. When the beef industry has said, hey, we want to potentially lower our emissions by 30%, that tends to be a pretty solid number. So last talk I want to just briefly show you and finish with a few slides is a paper that we just had published in Frontiers maybe a month ago, comparing, looking at a regenerative farm and looking at all the different outputs of that farm, a stacked enterprise model. It's actually in Bluffton, Georgia. Basically, their approach is the rancher will take degraded cropland And the first thing he'll do is bring a lot of hay from offsite onto that place, and he'll graze it, let cows stomp it in there to try to get some biology back into it. They'll fly seed, typically like a Bahia C4 type mixture of grasses, back into those fields, and then we'll slowly begin to graze it, get grass growing, and over time we'll bring in other types of livestock, poultry, even sheep and goats. And so what we did in this project is we did a few different things. I worked with Qantas, who's a private company that does LCA work. General Mills sponsored this study. And effectively what we did is twofold. We looked at the entire life cycle assessment, the carbon in and the carbon out of the entire model. And we also did a 20-year chrono sequence, such that we went into some areas that might have been still in a farming mode, all the way up to areas that it might have been in a grazing model for 20 years, okay? And we looked at the amount of carbon and soil health that was built across those systems. So we also, again, like my prior study, we incorporated carbon into the footprint. So what did we find? Again, this is one farm. Chrono sequences also can be a little bit touchy because we don't know for sure if every site that we measured on was treated the exact same. So there's qualifiers to this. It's not just always like a slam dunk case. But what we did find is when we went into those degraded cropland acres, we found carbon around 10 tons, which is really low. And we found that those could rise based over time across the farm up to even as high as around 60 tons. And this site right here was the oldest site on the farm. Importantly, it had no other animal impact. It had no poultry, it had no pigs, it had no compost, it had not had hay like spread across it in a very long period of time. So in a way, the line almost looks like it could be quadratic. We chose to just kind of keep it a linear model based on the fact that we knew that this site and these two sites were considerably different. The point, though, is that we saw about 2.29 metric tons of carbon per hectare per year. We adjusted for clay content as a covariate in this model. And then likewise, when we looked at several soil health indicators using the Cornell test, we found that most of them, interestingly, not water holding capacity, I think it has to do with the test, all rose even potentially exponentially. Our active carbon went from 80 to 844. Microbial respiration went up as well. And so super, super interesting types of outputs. What we also did then is we looked at the model from a CO2 equivalent per carcass weight in two different ways. We looked at it with and without soil carbon. So the blue represents commodity. The green represents what I call a multi-species pasture rotation. And we found that almost in any situation compared to a commodity model, the regenerative model, this MSPR, had about twice the emissions. Beef, maybe not as much, but pork and poultry, it did. It's the same things, right? We're comparing this model to a model that is very highly intensive. It's got a lot of fossil fuel being functioned through it, compared to a model that's more extensive, perhaps, but it is much more ecologically, I think, potentially regenerative as well. So there's give and take. What we found when we looked at all the different types of livestock, the net emissions fell dramatically, okay? It went from around 20 CO2 equivalents down to about 3. And so really found some interesting dynamics there. Again, there is the green being the MSPR, the blue being commodity. Land, a lot more land needed again. So we need to be thinking how this happens. I tend to push back on the land sharing sparing concept that, and no, not to say that there isn't things to talk about, that somehow this farm in Georgia, amongst just a sea of degraded land, somebody that's figured out a way that can hire people, that can produce livestock, that can rebuild soil, is somehow altering what's going on in the Amazon. And we tend to make these really global causal types of relationships. And I think that again, we need to be mindful of the global impact of our decisions here in the US. But I think likewise, I think that we need to be careful that these things don't get too misconstrued at the same time. A couple last things and I'll open up for questions. One of the things that we really get a lot are the aspects of carbon stabilization and saturation. A good colleague of mine, we're working on another project now. Dr. Francesca Catrufo at CSU has actually worked on what she calls the MEMS model. But the thing I want to break out is that she's actually begun to do a lot of work in terms of fractionating soil organic matter. We know that the mineral associated organic matter is the smaller organic matter that binds, it's a smaller mineral that binds organic matter, binds carbon. It's typically much more protected. The blue represent grasslands, the red represents forests. Typically we'll find is that about 65 to 70 or so metric tons of carbon per hectare, that type of organic matter begins to saturate. Forests, we see the same thing. However, there's more than one type of organic matter in the soil. In this case, there's also a larger aggregate, more labile, and you have to be careful. So again, its stabilization can be more, a little more delicate. But you also see that in her studies when looking at grasslands throughout Europe, that particulate organic matter continues to build. It goes and goes. It can get as high as, in these cases, 100 metric tons per hectare per year of carbon. So what the math basically says is only when you're starting to see like 8 and 10% organic matter in soil do you begin to see mineral or associated organic matter saturate. And then even after that, particular organic matter, again, can continue to build and doesn't shut off. So can it happen? Of course. I would also argue that a majority of our soils are so extracted right now that it probably is something we shouldn't worry about in the next 20 to 50 years. Where are we headed? We've got to continue to monitor. Where we're working on is models of working with Francesca and many others, not only measuring fractions of soil carbon, but also linking these up to gas flux, atmospheric fluxes, as well as remote sensing. So we can get better at measuring these ecological services in time and space, and therefore be able to have more objective models that can predict the actual outputs of what our decisions make. Right now, there's a lot of throughput right now. We see the ecosystem service market, Indigo Ag, Nori is another company that's out there. And so it's important that we see that we're able to measure this stuff better. We've poked a lot of holes over the last decade, and there's a lot of variability spatially and time and how you handle these samples. And we've got to get considerably better at measuring this stuff before we move it to this point where I think we start to see these carbon markets go. Another big challenge, I think, is the fact that today, oil industries and others, if you look at the price of carbon in oil, it's about 400 a ton. Typically, farmers are being paid about 15 to put it back. So there's a really big shift, right, that has to happen, I think, to make carbon a more monetizable type of commodity. It's not there yet. I think that it's important, though, that we develop strategies that can reward farmers for being more ecological, for building carbon in their soil. I think that they're standing on such an opportunity and solution. And that work is really brought together by what Keith Postian put together here the last year and a half or so, just showing these opportunities that we have to build carbon in agriculture, right? I think it's going to be a combination of private industry as well as public entities pushing this forward. But there are a lot of opportunities that I hope that are out there. So I think carbon is one metric. I also want to emphasize the fact that we can't lose sight. I would much rather try to measure water and evapotranspiration than carbon any day, that there is a multitude of metrics that are important when it comes to ecological resilience. It isn't about carbon. It shouldn't be, but it is, unfortunately. It's a lot of other things. I think these changes as we come about from the principles that improve these types of aspects in our soil, they've got to be fostered by land management. We've got to get better in terms of the technical aspects of measuring them. I think the time is now to try to push a lot of these things forward. So I feel like I went a little long, and so I apologize, and I'll stop at that. Thank you all.